Good morning, all. Write your name in the chat box. Screen is visible. Yes, screen is visible. Anyone tell me? So we will start.
Yes, sir.
Okay, so last two lectures, we started this chapter halogen derivatives. We completed the classification part, then methods of preparation of alkyl halides. And today we will start this physical properties of alkyl halides. So physical properties, no any question it is asked for the board examination, but for the CET, for the competitive examinations, 100% the question it is asked on this part. So these are volatile compounds. Volatile means these are having the very less boiling points. Easily these are evaporated. That is called as volatile compounds with sweet smell. They are having the very nice smell, fruity smell or sweet smell. You know the smell of nail paint remover like acetone. All these alkyl halides having the sweet smell. Then lower members are gases. Means when the 1 carbon, 2 carbon, 3 carbons, these are the lower members, and higher members means more than 15, 16, 17 carbons. These are liquids or solids. This is about the lower members and higher members. Then the nature of intermolecular forces. The bond between carbon and XC. We are discussing the physical properties of alkyl halide, that is R and X. We can take the example of this CH3F. So the bond between this carbon and X, that is general halide, it is a polar covalent bond. Why it is polar? Because of this fluorine, chlorine, bromine, iodine. These are all these are electronegative. And so as this fluorine, chlorine, bromine, and iodine, these are electronegative. What happens? They pulls the electron towards itself and got the negative charge. So the bond between carbon and X is, we can see clearly. It is shown. I will also show with the help of this highlighter. We can see this is the delta minus charge. X having the delta minus charge and this carbon having the delta plus charge. So the bond become polar. This CX bond becomes polar. So the alkyl halides are moderately polar in nature. Remember, moderately means these are not completely polar, but slightly these are polar compounds. And all of you know the size of this fluorine, chlorine, bromine, iodine as we move from top to bottom, this atomic size increases. So due to what? This bond become weaker. CH3I, this bond is very, very weak bond. We can see here, the bond length is very large here. 4214 picometer. This is the bond length of CH3I bond, and we can see clearly it is given in the table 139 picometer. Means this bond length is very small. So as the bond length is very small, the bond is very strong. And the bonds becomes weaker as we move down the group. CH3I, it will be easily broken. We can see the amount of energy required is very less here. 234 kilojoule per mole. This is the unit of bond enthalpy. Remember this unit, kilojoule per mole. So this much amount of energy is required to break this bond, means lower energy is required. And if you consider this CH3F bond here, see the energy is 452 kilojoule per mole. Means this bond is very strong bond, this bond is very weak bond. So this is about the nature of intermolecular forces. Okay. Then the next one is boiling point. Next physical property is boiling point. Higher the molecular weights of the molecules, higher the boiling points. Now anyone tell me here, CH3I, then here is CH3Br, CH3Cl, and CH3F. So all of you know this iodine having the more molecular weight. So this CH3I having the highest boiling point, then CH3Br, then CH3Cl, and then CH3F. This is because greater the size of the molecule, this is a very larger size because of iodine. Greater the size of the molecule, force of attraction is increases, and that's why the boiling point is increases. This is the reason. But in case of isomeric alkanes, all of you know what is mean by isomers, means the molecular formula is same, but the structure is different. So in such cases, in case of isomeric alkanes, what is happen? The boiling point of the alkyl halide decreases when the branching increases. Anyone can tell me why this is happening? Yes, Sudhanshu? Sudhanshu Redekar, what is the reason behind this? Why the boiling point decreases when the branching increases? Anyone? Anybody knows the reason of this? Akanksha is there? No one? Because I will explain. Because when the branching increases, surface area decreases. See, when the surface area decreases, the van der Waals forces decreases, and that's why the boiling point decreases. This is the reason. Then one problem is given here. Arrange the following compounds in order of increasing the boiling points. Chloroform is given, then chloromethane is given, dichloromethane, and bromomethane. I think methane. Spelling चुकले. So we have to arrange chloroform. Anyone tell me what is the formula of chloroform?
CHCl3.
Very good. CHCl3. Chloromethane, CH3Cl. It is also called as methyl chloride. Chloromethane is also called as methyl chloride. Then this is a dichloromethane is CH2. Dichloromethane means there are two chlorines, CH2Cl2. CH2Cl2. This is dichloromethane, and this is bromomethane, means CH3Br. CH3Br. So we have to arrange, and this is CHCl3 chloroform. We have to arrange this in increasing order of boiling point. So there are 3 chlorines, only 1 chlorine, 2 chlorines. So the order is given here, CHCl3, because the rule behind the boiling points, higher the molecular weight, 3 molecules are there. That's why this is having the more boiling point. Then there are 2 chlorines, and this chlorine and bromine, because this is CH3Cl and this is CH3Br, because bromine having the higher molecular weight, its boiling point will be more, and last will be chlorine. So such type of questions, it may be asked for the examination for 2 marks. Arrange this to make a practice of this. Then I'm coming to the solubility. As you know, the bond between the carbon and halogen is moderately polar bond. So these alkyl halides are insoluble in water. Remember, this property is very important. These are insoluble in water. They didn't dissolve in water. So if these are not soluble in water, ultimately these will be soluble in organic solvents, 100%. So these are soluble in organic solvents like ether, hexane, and benzene. Likes dissolve likes, remember this statement. Polar compounds dissolve in polar solvents, non-polar compounds dissolve in non-polar solvents. So this is about the alkyl halides. I am talking about the alkyl halides. Same properties are applied to the aryl halides. Aryl halides are also insoluble in water, but these are soluble in organic solvents. The properties are same, solubility, regarding the solubility. But in case of isomeric dihalobenzene, this is very important as for the CET. Please concentrate. Isomeric dihalobenzenes. One example is given here. This is a 1,2. This is ortho. This is 1,3 meta dichlorobenzene, and this is para dichlorobenzene. If you observe the boiling points are nearly same. Means 1 or 2 degree or 3 degree difference is there. This is 453 Kelvin. This is 446 Kelvin, and in case of para, it is 448 Kelvin. So the boiling points are nearly same, but if you observe the melting point, this is 256 Kelvin ortho dichlorobenzene, then meta dichlorobenzene is 249, and this is the, we can see higher melting point in case of the para dichlorobenzene. So this question is asked for the CET. Why this is para dichlorobenzene having the more boiling point? The reason is symmetry. See, the reason is symmetry. This is a symmetrical structure. We can see here chlorine and chlorine. So due to this symmetrical structure, what happens? The intermolecular forces of attractions are stronger. The reason is given here. See, this is because of its symmetrical structure, which can easily pack closely in the crystal lattice. And due to this, intermolecular forces of attraction are stronger. Therefore, more energy is required to overcome the lattice energy. So this is the reason why the para dichlorobenzene having the more boiling point, remember. Then next part is physical properties are completed. There are only 3 physical properties: melting point, boiling point, solubility, and nature of intermolecular forces. 1 mark question can be asked on it, or for the CET, 100% question will be there. Now I'm coming to the optical isomerism in halogen derivatives. This is the heading. In this chiral carbon, please try to understand what is the pronunciation of this. This is not chiral. This is called as chiral atom, and the molecular chirality, not chirality. So many students I observed, they makes the pronunciation like chiral. So this is not chiral. This is called as chiral. So it is very important question regarding the board examination for 1 mark, remember. So make it very IMP. For 1 mark VSA, very small type of answer question, this can be asked. So what is chiral carbon? Remember, a carbon atom. See, first I will show with the example. This is the structure of lactic acid. Lactic acid having the formula. This is the formula of lactic acid, CH3. I'm writing, please note down. This is the CH3, C, and this is COOH, C double bond O, OH, or we can write COOH directly. And here is H and OH. So this is the formula of lactic acid, CH3, CHOH, COH. So this is the carbon atom which is shown with this asterisk mark. We can see clearly. This mark is called as asterisk mark, and to this carbon, the 4 different groups, functional groups are attached. Okay. Different groups are attached. This is COH, this is hydrogen, this is CH3, and this is OH. When such type of carbon is there, to which 4 different groups or atoms are attached, not I use functional group, not necessary of functional groups, any different groups, any 4 different groups are attached, it is called as chiral carbon. So, and it is shown with this mark, this is called as asterisk mark. So when a molecule having this chiral carbon, there is one property. When the molecule having this chiral carbon, they having the unique property, that property is called as optical activity. Optical activity means when the chiral carbon is present in the molecule, it is optically active. Now I will explain what is optically active. These are non-superimposable mirror images of each other. So the example is taken here. Anyone can tell me what is this? What is this compound? CH3, CH, C2H5, and Cl. How many carbons are there? 2, 3, 4. So this is a butane. 1, 2, 3. Yes, on the second, this is carbon number 1. This is carbon number 2, 3, 4. Okay, this 1, 2, and this is 3 and 4. On the second carbon, the chlorine is attached here. So the name is 2-chlorobutane. It is shown here. The name is given here, 2-chlorobutane. So this is 2-chlorobutane. This is optically active, and this is the chiral carbon. All of you know why this is chiral, because the 4 different groups are attached. CH3 is different, this hydrogen is different, this C2H5 is also different, and this chlorine is different. So this carbon is chiral carbon. And you know the property, when the chiral carbon is present, it is 100% optically active, means when the mirror image is taken, suppose this is a mirror. So suppose this is a mirror and this is the image, mirror image. So if you pick up this molecule and put on this, these cannot be matched. These cannot be matched, because if you imagine you pick up this structure and put on this, means the carbon it will be matched, CH3 it will be matched, but this chlorine it will be not matched, hydrogen it will be not matched, C2H5 it will be not matched. So it is shown here in this diagram below. In this diagram show, so this is the Cl of this molecule, this is the Cl of this molecule, it will not match. So such type of mirror images are called as non-superimposable mirror images. That mirror images cannot be matched each other. And if such type of non-superimposable mirror images are there, that compound is optically active. Remember, in the next part I will explain optically activity means what. So the relation between the chiral molecule and its mirror images is simple. These are non-superimposable mirror images. Another mirror images are shown here for your understanding purpose. Now tell me, these are the mirror images shown here. These are the mirror images. If you put this glass on this glass, it will be perfectly matched. If this is one what you can say, this is one object which is circular, if you put on this object, it will be matched. So these are non-chiral. These are non-chiral because these are non-superimposable mirror images, not superimposable. They can superimpose, they fits on each other. They fits on each other. So these mirror images are superimposable. What you can call these images? Superimposable, means which fits on each other. And those mirror images which cannot be fit on each other, it is called as non-superimposable. We can see this is a left hand side and this is the right hand side. Okay, these are the two hands. Okay, one is left hand side and one is right hand side, which cannot be fit on each other. So this is called as non-superimposable mirror images. So the same like left hand foot and right hand foot, these are called as chiral objects. These are chiral objects, non-superimposable mirror images, and these are non-chiral objects, superimposable mirror images. So 1 mark or 2 mark question can be asked, what is chiral carbon? And they can also give some compounds, which of the following are so such type of question can be asked for the examination. Identify the chiral and achiral molecules in each of the following pair. Okay, now you tell me this compound, first one, this first one and second one. These are the pairs are given. Yes, tell me. First, tell me this is chiral. This carbon is chiral carbon. This
Yes.
carbon is chiral carbon
Yes, sir.
because 4 different groups are attached here. We can see HOH, Br, and CH3. So this is also chiral. So these are the pairs 1 and 2. 1 and 2, these are the pairs. What we have to do, identify the chiral and achiral molecules. Only we have to identify. So this is a chiral. One is chiral, then second one is also chiral. Third one, sorry, in the second example, this is second example. This is the first example. This is the first compound, this one. This is second, again 1 and 2. Yes, which is chiral?
Sir, in second, first one is chiral.
This first one is chiral. This is not chiral. This is not chiral, na? This is not chiral. Clearly see, because this carbon, we can say this carbon, these are the two same group. This is CH2 is same, and this CH2 is same. So this is not chiral, remember. This is chiral because this carbon having the 4 different groups, hydrogen, OH, CH3, and here is CH2. Okay. Now in this third compound, there are two again structures are given. This is 1 and this is 2. So which is chiral in this? This one. This one is chiral because this carbon is chiral. See, this carbon is chiral. I will show. So this is one CH3 group, one bromine is attached here, and one hydrogen is attached above, and this C2H5. This is C2H5. So this is having the chiral carbon, and this is not having the chiral carbon. So you understand such type of questions can be asked for the examination. Identify the chiral molecule and achiral molecules. So you understand what is chiral and achiral. Only we have to identify the 4 different groups. Okay. Then the next part is ordinary light. So no any question it is asked on the ordinary light. Don't worry about the definition. You must know the ordinary light. If you understand the ordinary light, then it is very easy to understand what is the plane polarized light. So ordinary light, all of you know, it is white in color. And this is actually the physics part. The ordinary light consists of electromagnetic waves. Remember, ordinary light consists of electromagnetic waves, and they having the oscillations up and down in oscillations of which field? Electric and magnetic field in all possible planes. This is the very important thing. So ordinary light having the electromagnetic waves, having the oscillations of electric and magnetic field in all possible planes. So see, this diagram is shown here. This is a cross section. It is taken of the ordinary light. It can oscillate like this, it can oscillate like this, it can oscillate like this, in all possible direction it can oscillate. So this is called as ordinary light, which is having the definition is given here. Okay, in which the oscillations of what? Electric and magnetic field in all possible planes perpendicular to the direction of propagation of light. This is very important condition. Perpendicular to the direction of propagation. Suppose this is the direction of propagation. Suppose this is the direction of propagation of light, and this is the ordinary light. It can oscillate like this, it can oscillate like this, it can oscillate like this in all possible direction, and it is shown here how it is rotates. Now this ordinary light, if it is passed through the Nichols prism, Nichols is the name of the scientist William Nicol who prepared this prism. This is a particular type of prism. It is prepared with calcite crystals. When the ordinary light is passed through the specific type of Nichols prism, what happens? This very interesting observation. It is found by this scientist. Oscillations are only in one plane. See the magic. When the ordinary light is passed through this particular type of Nichols prism, and see the magic, it only rotates in one plane, oscillates in only one plane. Suppose this is the direction of propagation of light. So it will oscillate like this only, like this, up and down, up and down. So this is the cross section of the plane polarized light. So how to prepare the plane polarized light? Ordinary light only we have to pass through the Nichols prism, we get the plane polarized light. This is very simple experiment. And you also remember the definition of plane polarized light, because it is asked for the examination for 1 mark. Define plane polarized light. So we have to write down, when the ordinary light is passed through the Nichols prism, oscillations only one plane emerge out. Such light having the oscillations in only one plane, perpendicular to the direction of propagation of light, it is called as plane polarized light. Do not draw this diagram. Diagrams is not required for the definition purpose. Only we have to write the definition. Okay. Then you understand ordinary light and plane polarized light. What is the difference? Only oscillations. So oscillations of what? Electric and magnetic field in all possible direction in case of ordinary light, and in case of plane polarized light, it oscillates in only one plane. Now I am coming to the optical activity. Just I explained this, introduced this word at the time of chiral carbon. When the chiral carbon, the molecule having the chiral carbon, it shows the property of optical activity, remember, always. So what is this optical activity property? This is the plane polarized light. Now this plane polarized light is prepared by ordinary light. Okay. This plane polarized light, when it is passed through the substances, certain substances, we don't know which substance is kept here. So see the definition, the property of certain organic substances by which it rotates the plane of polarization of incident plane polarized light, it is known as optical activity. This is the very difficult explanation is given. I will explain in simple languages. When the plane polarized light is passed through the certain substances, the entire plane of plane polarized light is rotated either right hand side or left hand side. That compounds are called as optically active. Means, again I will elaborate. Suppose this is a plane polarized light. We don't know which substances are kept here. If this plane is rotated, we can see this is rotated. This is the angle theta. This is the theta angle, which is rotated to the right hand side and which can rotate to the left hand side through the angle theta. So this is the angle is given here, angle theta. So if this rotation takes place either right hand side or left hand side, don't worry, or is written here, or. So ये rotation किसका है? The rotation of plane polarized light, we can see here. This is the plane polarized light when it is either rotated to the right hand side or left hand side. It is called as, this compound is called as optically active. And if the plane polarized light didn't rotate right hand side or left hand side, it remains as it is. The compounds kept here are called as optically inactive compounds. Remember, optically inactive compounds. So you understand what is optically active compounds and what is optically inactive compounds, how to identify. There are two options. There are two options. First option is You must know the structure of that compound. If the chiral carbon is present, then it is optically active. If otherwise, what is the second option? We have to pass the plane polarized light. We have to pass the plane polarized light, and we have to check either the plane is rotated to the right hand side and left hand side. If it is rotated, then it is optically active. So there are two main criterias we can identify whether the molecule is optically active or not. First one with the help of structure, second one with the help of light. We have to pass the light, and you must know the structure. Okay, you understand how to identify the whether the molecule is optically active or not? Anyone tell me? You understand? Optical activity is very important concept. By two methods you can check. First method is what? See the structure. Means you must know the structure of that compound. If the chiral carbon is there, then it is optically active. If you don't know the structure, we have to pass the light. So when the light is passed and this plane is rotated to the right hand side or left hand side, then 100% it is optically active. And if the plane is not rotated, means if this is a plane polarized light, it is passed and it will remain as it is, means the diagram will be same like this. No rotation. No rotation. This will be optically inactive. Means this plane polarized light comes out without any rotation. So depending upon the rotation, there are two types of compounds, optically active compounds. So the definitions are given here. Optically active compounds, the compounds which rotates the plane of plane polarized light. Just I told you the examples are given. Glucose is optically active because see here, glucose is taken here. Lactic acid, it is optically active. 2-chlorobutane is optically active because all these contains chiral carbon. Those compounds which do not rotate the plane of plane polarized light is called as optically inactive compound. So water is optically inactive. Ethanol is optically inactive. 1-chlorobutane is optically inactive. Ethyl chloride is optically inactive. Tertiary butyl bromide is optically inactive. Why these are optically inactive? Because of two reasons. They do not having the chiral carbon. You can draw the structure of all these water, ethanol, 1-chlorobutane, ethyl chloride, tertiary butyl chloride. See, check carefully whether the chiral carbon is present or not. And what is the second method? Pass the light. Which light? Plane polarized light. When the plane polarized light is passed through the water, ethanol, 1-chlorobutane, ethyl chloride, tertiary butyl bromide, you cannot observe the rotation here. It will remains as it is. The plane polarized light will oscillate in only one plane. No rotation it will be found. So these are the very, very important concepts: chiral carbon, optical activity, optically active compounds, optically inactive compounds. Then next part is explain the optical activity of lactic acid. Many times this question is asked for board examination for 2 marks. So if it is asked for 2 marks, what we have to do? First, draw the structure of lactic acid. This is the structure of lactic acid. Second time I am showing you this COH group, OH group. You can show OH above and below. Don't worry. But this carbon we have to show with this asterisk mark. It is chiral carbon because these are 4 different groups. COH is different, OH is different, CH3 is different, and H is different. Now, how many chiral carbon atoms are there? Anyone tell me? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 0. Yes. How many chiral carbon atoms are there in this compound? आवाज येत नाही का रे? एक मिनिट.
सर्वांना
आवाज येतोय ना माझा व्यवस्थित?
हो.
झोपलेत का सगळे?
हो सर येतोय.
एक तर सगळे झोपलेत. व्हिडिओ ऑन करा बरं जरा, मला बघू दे सगळे. स्टार्ट युअर व्हिडिओज. एक मिनिट, मी अलाउ करतो ऍक्सेस. स्टार्ट व्हिडिओज. निखिल पाटील दिसतोय मला. बाकीचे कुठे आहेत? ठीक आहे. चौगुले इज देअर, सुतार इज देअर, कोटी इज देअर. सगळ्यांना बघतो जरा मी. झोपले कोण कोण मला बघू. बाकीचे कुठे आहेत अजून? गोडांबे, स्टार्ट युअर व्हिडिओ. प्रेम, चितळे, हा. बाकीचे कुठे आहेत अजून? 1 मिनिट. हर्षल बिडकर, यश, धवल, क्षीरसागर, मराठे.
सर ऍक्च्युली माझा कॅमेरा डिसेबल्ड आहे, तुम्ही स्वतःहून पाहू शकता.
ओके, म्हणजे तुझा आवाज येतोय म्हणजे तू जागा आहे. येस, अथर्व मगदूम, शिंदे, केतन लाडे, शर्वरी तुपे, हे सगळे ऐकतायत का? आवाज येतोय? नुसतं कॅमेरा ऑन ठेवून बसायचं नाही तिथे, आपलं माईक ऑन ठेवून. यू हॅव टू पार्टिसिपेट इन द लेक्चर. ओके, switch off your videos because the internet connection, it requires bandwidth कमी होते ना त्याची. So what is my question? This is the compound having only one chiral carbon, only one chiral carbon. This is shown with this asterisk mark, and one formula is there, 2 raised to n, 2 raised to n, where the n indicates the number of chiral carbons. That is 2 raised to 1 means the answer is 2. We get the answer, and this 2 indicates there are 2 optical isomers here. 2 optical isomers. This is one optical isomer and this is another optical isomer of lactic acid. The plane, it is shown. So we don't know which is dextrorotatory and which is leo-rotatory. I introduced these 2 concepts, new concepts, dextro and leo-rotatory. I will explain. When the plane is rotated to the right hand side, remember which plane? That plane polarized light's a plane. When that plane is rotated to the right hand side, suppose C, this is rotated to which side? Right hand side. When such type of right hand side rotation is there, this is called as dextrorotatory compounds. And when it is rotated to the left hand side, it is called as leo-rotatory compounds. So either compound 1 is dextrorotatory, compound 2 it may be dextrorotatory, we don't know. So for the 2 marks, this is expected. What is expected to after 1 minute again we have to join, remember, because only 1 minute is remaining. Again 20 minutes we have to continue the lecture. So we have to draw the structure, we have to write the number of possible isomers, and we have to draw the structure. We will get 2 marks here. Okay, this is the optically of activity of lactic acid. And now the terms. Optical rotation, this theta, angle theta is called as optical rotation. Just I explained. Optical rotation is denoted with angle theta. Here it is denoted. This is the rotation. This is the optical rotation. It is denoted with this angle theta. Then dextrorotatory, just I explained. When it is rotated to the right hand side, it is called as dextrorotatory, and it is shown with the symbol D or plus sign. D or plus sign, it indicates dextrorotatory. And opposite to this dextro, leo-rotatory, it is denoted with a small l or minus sign. So minus sign indicates it is leo-rotatory, which is rotated, means that plane of plane polarized light is rotated to the left hand side. Okay. So these definitions can be asked for the examination. Define optical rotation, define dextrorotatory compounds, define leo-rotatory compounds, define chiral carbon, define optical activity. For the definition purpose, all this is important. Okay. Now the next point is enantiomers. Enantiomers. So you have to join again.